All right, Math 2, here we go. We got lesson 9.1.4, transforming the absolute value function. All right, so first we're going to just look at the absolute value in general. This is the parent function, the absolute value of x. So looking at this one, when we're looking at what we're putting into it, what are we putting into it to get 9 to come out? Well, we got to look at it as thinking that there are actually more than one thing that we can get. So we've got, this is kind of done kind of goofy, but it's supposed to say 9 up there. So if 9 goes in, absolute value of 9 is 9. If 7 goes in, absolute value of 7 is 7. If root 2 goes in, absolute value of root 2 is root 2. So it's the same, except for over here. If negative root 2 goes in, we get positive root 2. So here I've got the same output for different inputs. So with absolute value, you're going to get different, the same output for different inputs. Not all the time, but it's very similar to the quadratic function, where you get those two, when you have your axis of symmetry going, right down the middle, that on either side that they're mirror images of each other. So look at this one, determine the missing inputs and outputs for the function machines. Okay, so our output is 4. So what could have we put in there to get? Well, we could have put in there 4, but also you have to remember that if you put in a negative 4, that it will also give you an output of 4. So there's two inputs that work for that one. If I've got negative 16, there is only one output I could get, positive 16. If I've got an output, there are two inputs that we can put in. Positive 9 and negative 9, because they'll both give me 9 as an answer. Over here, I've got negative 3. That's not possible. Our outputs always have to be positive when we have an absolute value. So this is not possible. So there are no inputs that would give us a negative 3 outputs because the absolute value always makes it positive. So if you are given an output, how do you find the inputs? So if we're given an output, basically, here we were given an output of 4, we can just take the positive and negative of the output. So the output and the opposite of the output. The inputs are the positive, or are the output, and the opposite of the output are the output and the opposite of the output. All right, next we're going to go ahead and graph this parent function, f of x equals x, the absolute value of x. So let's think if we plug in 0. Well, there's only one output for 0, we would get 0. So there's my first point. Next, what if I plugged in 1? Well, if I plug in 1 here, I would get 1. But also, if I plug in negative 1, I would still get 1, because remember, the absolute value changes it into a positive. If I would plug in 2, I'd get 2. If I plug in negative 2, I'd get positive 2. And over here, 3 would give me 3. Negative 3 would also give me 3. 4 would give me 4, and negative 4 would give me 4, and so on and so forth. So here we've got our absolute value graph, and it makes this V shape. Oops. Makes a V shape right there. We can see here that the reason why this last one wasn't possible was because here our graph never makes it into the negative territory. Our y value can't be negative 3 because our graph never makes it to where negative 3 is over here. So our range for this one would be 0 or anything bigger than 0. Our domain is all real numbers. Meaning that I can plug in anything that I want into x, but my output is limited. Oof. There you go, that's better. So my output is limited. Here I can see that my output's my y values. I can have y values up here and equal to 0, but I can never have negative y values. Over here we said that that wasn't possible. So we would say that our y values have to be bigger than or equal to 0. So that would be our range for that one. Now, absolute value functions can be transformed similarly to how quadratic functions were transformed. So remember when we moved the vertex, inside of the parentheses, we did the opposite of that number. So like if it was x minus 2 inside the parentheses, we knew that meant go right 2. So the same thing happens for our absolute value functions. So we'll just call this one f of x. So this one says that move the vertex left 2 and make it face down. Well, how did we make it face down with quadratic functions? We put negatives outside the parentheses. Well, now we don't have parentheses. Instead, we have absolute values. So we're going to do the absolute value sign here. Left 2, so if we want to go this way 2, that means that I would add 2 to the x. And since it's not going up and down, I don't add a number over here. So if I were to graph this, left 2, there's my vertex, and this is facing down. Now the parent function has a slope of 1. So this is slope of 1, this is slope of negative 1. So if we're going to stick with the parent function, we're going to have that same width to our V shape here. All right, so this one shifted to the left 2 units, and then it's facing down. So compared to the parent function, it went over 2 units and then face down. The face down was achieved by putting a negative out here, and then shifting it over to, we do plus 2, remember, because it's always the opposite, just like we did when we did quadratic functions. Now the next one, we want to move the vertex right 2, so we want to go this direction 2, which means we're going to need a negative in here. And it's going to go up, right 3 and up 2. Now this one we also want to narrow the graph. We'll call this one g of x. So let's say we want to narrow the graph. Remember we needed a number bigger than 1 outside of the parentheses. So for absolute value, we'll put a number bigger than 1 outside the absolute value. Now this is going to go right 3. So that means I need to do x minus 3 inside of the absolute value. And then it's going to go up 2, so I would put plus 2 at the end there. All right, let's go ahead and graph it. So we went right 3, 1, 2, 3, because remember it's the opposite of this number here. So right 3 and then up 2. There we go. Now this one had a positive out here, so it's going to face up. But the 2 is going to make it be more narrow. Now this 2 actually is the slope. So here I would go up 2 and over 1, up 2 and over 1. Over on this side, I go up 2 and backwards 1, up 2 and backwards 1. So there's our V shape, and we can see, just comparing it to the parent function that's above, that this one is narrower, because we had that multiplier outside of the absolute value. So this is our descriptive form for absolute values. We can just look at it and see, okay, it's narrower, it's shifted to the right, and it shifted up. So these are all of our ways to change the parent function. All right, next page. All right, so here on this one, I can see that it went to the right 1. I can see that it shifted up 2. I can see that it faces down. And then let's look for the slope. It looks like this one goes down 2 over 1. So the slope is 2. So I'm going over here. I'm going up 2 over 1. So I got right 1, up 2. It's facing down, and the slope is 2. So this is more narrow than the parent function. All right, using that information, we need to write the function for that graph. Let's just call it f of x. All right, first of all, it faces down. I need a negative. It's more narrow than the parent function. So we said the slope was 2. It's going right 1, so I need to do x minus 1 because we do the opposite that it should be here. And then it's up 2, plus 2 at the end. Boom, we've got our equation that fast. So this descriptive form or this graphing form or this vertex form for absolute values is super fast way to graph these. So it's kind of nice to have it like that. All right, last one. Use the following function, this one, and find the x and y intercepts without graphing. Okay, so if I want to find the x-intercepts, I would plug in 0 for the y. So let's find that first. So I do 0 equals 4/5 absolute value of x minus 2 minus 2. So here I would add 2 to both sides. Next thing that I would do is I multiply by the reciprocal of 4/5, which is 5/4. So I'd multiply this side by 5/4. And I'd multiply by this side by 5/4. So over here I get 10/4, which is 5/2. So this is 5/2 equals the absolute value of x minus 2. So you can call it 5/2 or 2.5, doesn't matter. All right, so now it's an absolute value. So x minus 2 could equal that, but x minus 2, what if this number in here were a negative and it equaled that? So we're going to write two possibilities. X minus 2 could be positive 5/2 or 2.5, but x minus 2 could also be negative 2.5. Because if this number were negative, it would end up being positive 2.5. So if I add 2 to both sides, I get x equals 4.5. If I add 2 to both sides, I get x is equal to 1.5. No, 0.5. So I add 2 and I get 0.5. Add 2, I get 4.5. Those are my two x-intercepts. To find the y-intercept, I just plug in 0 for x. So I do 0 minus 2 and subtract 2. So over here, 0 minus 2 is negative 2. Next, I would change this into just positive 2 because that's what the absolute value does. And then 4/5 times 2 should be 8/5. And then 8/5, we can change that into a decimal to make this a little bit easier. And we'd get 1.6, I believe. And then 1.6 minus 2 would finally give me a value of, what's that, negative 0.4. So there's my y-intercept, negative 0.4. Here's my two x-intercepts, 4.5 and 0.5. Now we're going to graph that function. Well, the first thing that we can say is that we're going to have a vertex at 2, negative 2. So 2, negative 2. Does this face up? Yes, because that's positive. And the slope is 4/5. So I go up 1, 2, 3, 4 over 1, 2, 3, 4, 5. Up 1, 2, 3, 4, back 1, 2, 3, 4, 5. And that is how you graph it. Now take a look at our intercepts when we graph this. Okay, see how this is wider? That's because this number was smaller than 1. So that makes it wider. Now look at our intercepts. 4.5. Yep, there's 4.5. 0.5. Oh, this was negative 0.5. Oh, I missed that. So this is negative 0.5. That works. Y-intercept, negative 0.4. Yep, that looks about like negative 0.4. So it's all working out for us. All right, that's all I got for you. Math hard? See you later.